In this video, I'm going to walk you through electrochemical cells, and more specifically, we will focus on voltaic cells. We will learn how to set them up and how to calculate the voltage of one of those cells. So electrochemical cells here are just when you have these oxidation reduction reactions, and you're going to have energy being released by a favored reaction. In a favored reaction, we are going to convert that energy into electricity. Or we could use electrical energy here, electricity, to cause a non-favored reaction to occur. So these are just oxidation reduction reactions. If it's favored, we're going to generate electricity. If it's a non-favored reaction, we're going to use electrical energy here to cause that reaction to occur. If you were to place these reactants together for an oxidation reduction reaction, they would actually just collide essentially, and the electrons would be transferred, but there would be no useful work created here because the chemical energy involved would just be released as heat. So this is why if you want to actually create a useful current here, if you want to create electricity, you have to separate the oxidizing and the reducing agents here. All right, and then the electron transfer will happen through a wire instead of just generating heat. And then when you have the electron transfer happening through a wire, this is the creation of electricity essentially. So we separate the reactants. Otherwise, we would just generate heat here, and that's not the goal. We want to be able to create electricity. So you will see typically that these reactants are going to be separated in some way. There's two types of electrical chemical cells here that we can look at. The two types of electrochemical cells are galvanic cells, also known as voltaic cells, and electrolytic cells. We're going to focus more specifically in this video on the voltaic cells, but a galvanic or a voltaic cell is a thermo-favored chemical reaction. All right, this is a thermo-favored reaction. Essentially, it is a battery. It's generating electricity here. All right, whereas an electrolytic cell is a thermo-unfavored reaction. Because it is thermo-unfavored, you need some form of external power source here. You need some form of external current to make this reaction happen. So that's the big difference here between these two electrochemical cells. A galvanic or voltaic cell is thermo-favored and will generate electricity, but a electrolytic cell is thermo-unfavored and you will need electricity to make it go. There's other differences here between these two, but for now, this is the main difference between them. And like I said, we're going to try to focus on voltaic cells in this specific video. This slide is just showing you kind of the difference here between galvanic and electrolytic cells. If you notice, the one on the left is a galvanic cell. All right, this is generating an electric current. This is a thermo-favored reaction here. If you notice, there's actually a voltmeter here and it has a measurement on it because this specific cell is generating electricity essentially. But then the one on the right is an electrolytic cell. Okay, you are not generating electrical current. Notice there's actually a power supply there, right, that's plugged in. You are providing an electric current in order to force the reaction to take place because it is a thermo-unfavored reaction. All right, so this is the big difference between a galvanic cell, which is thermo-favored, generating electric current, and an electrolytic cell, which is thermo-unfavored, which you need to provide an electric current to make it go. There are a lot of terms here associated with these galvanic or voltaic cells. Remember, these are the thermo-favored cells. We need to be careful with all these terms, so you need to make sure that you know them. You could be asked, obviously, to use these terms, or you'll have to use these terms to answer questions here. So when we're talking about the anode is the electrode here where oxidation is occurring. All right, oxidation, if you remember, is the loss of electrons. So the anode can actually get smaller over time as these electrons are being lost. All right, so anode, oxidation. The cathode then is the electrode where reduction takes place. All right, reduction is the gaining of electrons. So this electrode can actually get larger over time. So you definitely need to know the difference between anode, which is where oxidation occurs, and cathode, where reduction occurs. Again, you got to know these terms. If you ever hear anything about an inert electrode, this is typically used when a gas is involved, or if we're going from ion to ion here instead of using a solid. So they use this inert electrode to kind of function as the solid here, if you will. It's typically made of platinum or graphite. You just need to realize that it's needed here because we're going to be using a gas or an ion instead of a normal solid, as you'll see. A salt bridge is very important, and we will talk more specifically about the salt bridge coming up, but this is used to maintain the electrical neutrality in the electrochemical cell here. It's a very important part of the electrochemical cell, and if you don't have it, the cell can actually shut down. So there's a lot of different salt bridge kind of ways you can kind of form this or use this. It could be filled with agar. You could use a porous disc. We kind of use a very simple version of a salt bridge in our lab, so we will talk about this, but it's definitely important and you need it to maintain the electrical neutrality here of the cell. The electrons flow through the wire from anode to cathode here. So that's a very important thing to understand. It's alphabetical order. It goes from A to C. So when the electrons are flowing in a galvanic cell here, a voltaic cell, it's going from anode to cathode. And then finally, a voltmeter here is just what's measuring the cell potential. Essentially, it's measuring the voltage here of your electrochemical cell, and it's going to do that in volts. So again, a lot of terms here, and you definitely need to know these terms. Again, another picture here of an electrochemical cell. This is a voltaic cell here. If you notice, the dead giveaway here is that we are generating an electric current from our voltmeter there. So this is a thermofavored reaction, and we are generating that electricity essentially. Remember here, you need to understand that the anode is where oxidation occurs. So the zinc side is labeled as the anode. That is where the loss of electrons are taking place. So you need to understand this again on a molecular level here. If you notice, you're going to have your solid zinc metal, and it's going to be losing electrons. All right, so you're going to form zinc 2 plus. So the zinc is going to slowly start to enter the solution as zinc 2 plus ions. And when that happens, the 2 electrons that are being lost are going through the wire. So you need to understand that at the anode, the loss of electrons are taking place. The zinc solid is becoming zinc 2 plus, and essentially it's entering solution. So over time, the anode where oxidation is occurring gets smaller. All right. As those electrons travel through the wire here and generate the current, they come over here to the cathode side. And you see the copper side here is labeled the cathode. This is where reduction takes place. Reduction is gaining of electrons. So the Cu2 plus ions here in the solution on this side are gaining those electrons and becoming solid copper here. So Cu2 plus is going to solid copper by gaining those 2 electrons, and you'll see that they actually leave the solution, the ions leave the solution and become solid copper, and it starts to plate on the piece of copper. So over time, the cathode gets larger because that's where the gaining of electrons is taking place, and the Cu2 plus from the solution is plating out as Cu solid. All right, you can see the salt bridge here, and we will be kind of discussing this more, but definitely you need to be able to actually understand the basic setup of one of these voltaic cells. You'll have to actually label all the parts, label the anode, label the cathode, label the voltmeter, calculate the voltage, show which way the electrons are going, show which way the ions are going in the salt bridge, and then obviously understand what's happening here all throughout the cell. So this is a very important concept, and we will talk about all this and how this is all set up. A little bit more here about the setup of these galvanic or voltaic cells. Basically, these metal electrodes are going to be placed in 1 molar solutions, and this is under standard conditions, that contain ions of itself, essentially. So for example, if you are using a zinc electrode here, and the zinc is going to form 2 plus ions, when it is being oxidized here, it needs to be in a 1 molar solution of something with zinc 2 plus. All right, so in this case, we're using 1 molar zinc nitrate here. Right, and same thing for the copper side. If you have a copper metal electrode here and it's going to be reduced from Cu2 plus, you need a solution, a 1 molar solution of Cu2 plus ions here. So essentially, it's going to be in a 1 molar solution of copper 2 nitrate here. So very important idea to understand. You will have these metal electrodes separated because that's how we're going to generate this electrical current. If they were together, right, it would just produce energy here given off as heat. We don't want that. We want the electrons to go through the wire to generate electricity. So we keep these electrodes separate. But the metal electrode needs to be in a 1 molar solution that has ions of itself in there. So if you have zinc, you need to be in a 1 molar solution of zinc 2 plus. All right, this is something you need to understand. And when we are drawing these voltaic cells, we need to actually label this and show it and understand it has to be 1 molar solution. And you can't have it empty. It has to be in a solution there on each side. So that's very important. Realize here, you might see platinum or graphite used as one of the electrons if we're not having a solid metal involved here. If we were using a gas or we were doing ion to ion, you might see platinum or graphite being used as the electrode. Just realize that's an inert electrode and we're using that because we are actually looking at something else like a gas or doing ion to ion here. So just be aware of that and definitely understand that these metal electrodes need to be in 1 molar solutions that have the ion of itself in there. I already said that there's a lot of terms here that you need to know. So there's some tricks to help you remember this. We said that the anode is where oxidation occurs. So a way to remember that is you can remember anox, okay? Anox, the oxidation occurs at the anode. You can use red cat to remember reduction occurs at the cathode here. This is something you need to be able to do. You need to know that the anode is oxidation and the cathode is reduction. So use anox, red cat, to help you remember that here. We also need to know that the cathode is positive and the anode is negative here in our voltaic cells. So a way to remember that is that we have the T in the cathode kind of functioning as a positive. Remember that cathode, the T, positive, the cathode's going to be positive here. The anode, the second letter is N. Let that stand for negative. All right, so the cathode is going to be positive, the anode is going to be negative. Use these little tricks to help you remember that. All right, you've got to be able to know the charge on each. You can use the little trick here called fat cat to remember that the electrons in a voltaic cell always go from the anode to the cathode. All right, the electrons go from the anode to the cathode here. All right, that's going to be the flow of electrons in a voltaic cell, and you need to know that. You need to be able to identify the anode and cathode based on oxidation and reduction, and you need to know that the electrons are going to flow from the anode to the cathode here. It's alphabetical, but you could use fat cat to help you remember that. I already mentioned this salt bridge, and we said it's used to maintain this electrical neutrality in the cell. But the basic gist here of this salt bridge, how it's maintaining this electrical neutrality, is it's going to provide ions that can balance the charge in the cell itself. All right, it's going to help maintain this electrical neutrality by providing ions to each side here of the electrochemical cell. Typically, it's going to be filled with a salt solution or agar or a paste here. A very good substance to use here is KNO3. You need to have a substance that has no precipitation going to occur with it. If you have ions kind of moving to each side of the cell here, if you aren't careful, you could cause a precipitate to form. Because remember, there's going to be solutions on each side here. In each electrochemical cell, there's solutions. So if you don't choose the right substance for your salt bridge, you could actually cause a precipitate to form. So one of the easiest substances to use is KNO3 because we know alkali metals here are always going to be soluble nitrates are always going to be soluble, so they would never cause a precipitate. Realize you don't have to just use KNO3. There are other solutions or substances that you can use in your paste here or the solution, but you want something that doesn't cause a precipitate. Maybe a porous disc is used instead. You can kind of see here that these two electrochemical cells are separated by a porous disc rather than an actual bridge. So in our lab, we actually will use a little piece of filter paper. You soak the filter paper in your solution that you're going to use, like your KNO3, and then you just drape it between the two cells, and that will allow the ions to flow through the paper, all right, to be able to balance the charge here, to maintain that electrical neutrality. So you need to know that when you have these voltaic cells set up, when you have this electrochemical cell set up, you must have the salt bridge separating the two here. You have to have this salt bridge going in to each of the electrochemical cells. If that's not there, this electrochemical cell that's set up will eventually shut down. All right, so this is very important. AP has asked questions about this before. You need to understand what its purpose is, why it's there, and you need to actually make sure that it is there in your setup, in your drawings, in your labs here. All right, so we need to pick something for our salt bridge that's going to be able to provide ions, plus and minuses, to balance the charge here in our electrochemical cell. But it needs to be a substance that does not cause a precipitate. Let's look at an example here of a voltaic cell. The first thing I notice is that I have a voltmeter here and it's generating an electric current of 1.10 volts. That's how I know this is going to be a voltaic cell. It's thermofavored, it's generating an electric current. So I know that this is thermofavored, this is a voltaic cell. You would need to potentially be able to draw this entire setup and label everything. So you better make sure you're paying attention here and seeing that you kind of need all this stuff in your picture, and you need to know, why it's set up a certain way and what's actually taking place. So the first thing I have here is you need to realize they need to be in separate containers here. Otherwise, we would just generate heat when they were reacting. We would not generate an electrical current. All right. It doesn't matter which side your anode and cathode are on. You just need to know which side is the anode and which side is the cathode. So if you're looking closely here at the actual half reactions, you can see here the zinc is going from zinc solid to zinc 2 plus. So it's losing electrons. Well, that's oxidation. And we already know anox. The anode is where oxidation is occurring. So this side would get labeled anode. All right. And then if you look at the copper side here, we have the Cu2 plus gaining 2 electrons to go to Cu solid. Well, gaining of electrons is reduction. Red cat, reduction is where the going to take place at the cathode. So we label this side cathode. You need to have your anode and cathode labeled. You need to know that your anode is negative and your cathode is positive here. All right. So then once you kind of know what's the anode and what's the cathode, you need to realize you need to have the solid metal itself in a 1 molar solution that has the ions here of itself. So this would be labeled as a 1 molar solution of zinc nitrate. All right, you would have to actually label that. You need to show that the metal, the anode here, the zinc anode, is in a solution of 1 molar zinc 2 plus. All right, you don't have to know that it's zinc nitrate, but you need to label that it's 1 molar zinc 2 plus solution. And then the copper, all right, the metal copper here would be in a 1 molar solution of Cu2 plus. All right, has to be in a 1 molar solution of the ion itself. So that would have to be there, and you have to have them both labeled. All right, so now we know that anode is where the loss of electrons are taking place, and the cathode is where reduction, the gaining of electrons. So immediately you know the electrons are going to be flowing from the anode to the cathode here. All right, remember fat cat, from the anode to the cathode alphabetically. So you actually have to show that. You have to show the electrons going in that direction. All right, and then the voltmeter here is showing the voltage of the cell as that's taking place. This switch is just controlling when it's on or off. It would either be open or closed. When it's closed here, all right, you're generating the electric current essentially. But then let's talk about this salt bridge. You would have to actually show your salt bridge here in the picture, in your drawing, in your diagram, all right, for this voltaic cell. So you can see here we have, it looks like a tube in this case. It could be anything. It could be just, a piece of filter paper draped between the two. We could get more fancy. But here we just have a tube, and it's filled with sodium nitrate in this case. Remember, it needs to have something that can form plus and minus ions, but that's not going to cause a precipitate here. Well, sodium is an alkali metal. It's never going to cause a precipitate, and nitrates are always soluble as well, so we won't have a precipitate forming on either side. But you need to know which way the ions are going to go, all right? And this requires a little bit of thinking here. So notice on the anode side, on the zinc side, you have to think about what's happening. The zinc in this case, the solid zinc, is losing electrons and forming Zn2+. So the Zn2+ is entering the solution. As the electrons are lost and going up through the wire, the solid zinc becomes Zn2+ and enters the solution. So think about what's happening here. As that's taking place, you have a large amount of zinc 2 plus, zinc 2 plus, zinc 2 plus entering the solution. You would have a buildup of positive charge on the left side. Well, that's not good. We need to balance that out. So from the salt bridge, the opposite charged ion is coming in to balance out that positive. So if we have a buildup of zinc 2 plus, the NO3 minus is going to enter from the salt bridge. And you would need to show that. You need to show that the NO3 minus is coming in to the zinc side here. But then on the cathode side with the copper, remember what's happening. The Cu2 plus is gaining the electrons that are coming through. All right, so the Cu2 plus is leaving the solution, all right, and plating out as solid copper. So you have positives being lost. You would have a buildup of negative ions occurring as the positive copper is being reduced. So the Cu2 plus is reduced to Cu solid, reduced, reduced, reduced. Buildup of negative charge, so you would need the positive ion, the oppositely charged ion, to come in from the salt bridge in order to balance out that large amount of negative that is forming, right? So this is a big idea. You need to know and show which ions are coming in to which side, and you need to understand why that is happening here, all right? So there's a lot of stuff that you need to understand from a picture here of a voltaic cell and be able to actually diagram this and show everything as well. Okay. And just an FYI here, what would happen if this salt bridge was removed? Let's just say you drew this with no salt bridge. Well, eventually here, this cell would just shut down. You would have too much positive on this side, too much negative on this side. The cell would just shut off. All right. So definitely big idea here. Take your time with this. Understand what's happening in a voltaic cell and be able to diagram it. This picture is showing that same voltaic cell we just looked at, but on a molecular level now. So you need to see here and you need to understand that on the zinc side, on the anode side, that's where oxidation is occurring or the loss of electrons. So you need to understand that the zinc metal is losing electrons here up through the wire. And then when that happens, it's entering the solution as Zn2 plus ions. But then on the cathode side here, on the copper side, that's where reduction is taking place or the gaining of electrons. So as the electrons kind of come through the wire, the electrons are going to be gained by the Cu2 plus ions that are already in the solution, and it's going to form Cu solid here. Essentially, the solid copper is plating out. So there's definitely a difference between the two here. The zinc solid is losing electrons, entering the solution as zinc 2 plus, but then on the copper side, the copper Cu2 plus in the solution already is gaining those electrons, forming solid copper. So you need to understand what's happening here with the flow of electrons, what's happening with the oxidation and reduction, and definitely understand this on a molecular level. I want to mention something here called shorthand cell diagram or line notation. So that cell we just looked at essentially, here is the overall balanced equation for that cell. We saw the solid zinc here and the Cu2 plus essentially becoming solid copper and zinc 2 plus ions that entered the solution. and the concentration of your solutions here were both 1 molar because it was standard conditions. If you want to write this in what we call line notation, what you do here is you always write your anode first, and then you write your cathode. So you're always going to have this set up kind of as the flow of electrons here from anode to cathode. So you put your solid here on the left, your zinc solid, then you put a single up and down line, that's indicating a phase boundary. That means that the solid zinc was sitting in the zinc 2 plus, but you need to label the concentration here. That solid zinc was sitting in a solution of 1 molar zinc 2 plus, all right? But you use this single up and down line to indicate that it's a phase boundary. This was a solid, this was a liquid here. And then that was separated by the salt bridge. So we show a double line, a double up and down line here to indicate that this was kind of in its own separate little container, if you will, and there was a salt bridge between them. And then you write the ion here of the other solution. So this was Cu2 plus 1 molar, and that was your copper solid sitting in that. So, big idea here. You have the anode written first. So the anode on the left, always showing the flow of electrons from anode to cathode. So it's kind of like your solid metal electrodes are on the ends here. They're like your bookends here. And then you show the phase boundary, put your 1 molar solution of the ion separated with a salt bridge. And then on the other side, you have your 1 molar solution of the ion right on the other side of the salt bridge. And again, the solid on the outside. So this is something called line notation. You need to be able to show this for a cell if you're asked to do the line notation, and you need to understand how it's set up here, right? Anode, then the cathode separated by phase boundaries and the salt bridges, and you do need to indicate the molarity here of your solutions. When you hear us talking about the cell potential, this is just talking about a measure of the electromotive force or the pull of electrons here as they travel from the anode to the cathode. All right, essentially, this is just called the cell voltage, and you might see this denoted as E cell or EMF or just called the cell voltage here. We use the volt, all right, or a capital V as our unit here of electrical potential. And the voltmeter is a device that measures this electrical potential. All right, and we will see this in a voltaic cell because we are generating an electrical current. So we need a voltmeter. Just something to keep in mind here that you are using or going to lose some of the energy here as heat when this is taking place. All right, this is called resistance. As the electrons are traveling through the wire, some of that energy is lost as heat. All right, this is resistance, which makes actually these voltmeter readings a little bit smaller than what you would actually calculate them to be. So that's kind of a thing here to understand. If you were to see this like in lab and you're trying to understand, well, why is my measured voltage, a little bit off compared to my calculated voltage, is because some of the energy is actually being lost as heat here. There's resistance. So definitely something you need to know and understand that that's why they could be off. All right, don't forget this. A little bit more here about this cell potential. You need to understand that each half reaction here will have an electrical potential. So you have an electrical potential associated with your oxidation, and you'll have an electrical potential associated with your reduction. And we measure each of these potentials against what we call a standard, all right, a standard electrode. We use hydrogen as our standard electrode here, and it's assigned a value of 0 volts. So essentially, everything is kind of measured and compared against standard hydrogen, which has 0 volts. And we will use standard conditions here of our cells typically, and that's going to be 1 ATM, 1 molar solutions, which we already know. Our solutions here have to be 1 molar, 25 degrees Celsius, and we use E naught of the cell here to denote that. So when you see E naught, you just need to know that, oh, that means we are under standard conditions here for the cell. I already said here that these cell potentials are going to be measured against the standard hydrogen. So we have a list of standard reduction potentials here. Something important to understand is that these half reactions are always written as reductions. So when you have a list of these standard reduction potentials, they are all written as they are gaining electrons. So you will have a list of this. You will see there's a list here in the notes. There is a list on my website that you can print, and you need to be able to use these. You don't have to memorize them, but you need to understand that they are written as reductions. So if you need the standard potential here for an oxidation, you have to flip or reverse the reduction, and then you have to flip the sign of the voltage as well. So for example here, if you're just looking at this standard reduction potential table here, if you were looking at PB4 plus, well, as a reduction, it forms PB2 plus in this example, and that's the potential, plus 1.67. But if you needed the PB2 plus here to be oxidized or lose electrons, you would need to reverse that, and the voltage would be negative 1.67. So very important. This is something that kids mess up all the time here. All right. You got to know that these are written as standard reduction potentials. And if you want the oxidation, you have to flip it and then flip the sign here of the voltage. The most positive ones on your standard reduction potential are the ones that are the most easily reduced. All right. So these are typically going to be nonmetals. If they're the most positive, they're typically going to be your nonmetals because they're the ones that are going to be the most easily reduced. They're going to gain the electrons the most. Makes sense. Nonmetals want to gain. The ones that are the least positive on your standard reduction potential table, these are the ones that are going to be most easily oxidized. They're going to lose the electrons here the easiest. Well, this would be your metals, which makes sense. Metals like to lose electrons. So the least positive are more likely to lose electrons. You can also use this actually as an activity series, understanding that the less positive metals here would be more active. So you can also use this kind of as a little activity series if you didn't have it as well. So this is something you need to understand here. We're given this list of standard reduction potentials. Sometimes they might just give you the reduction potentials right in the problem itself, but you need to understand that if you want the oxidation, you have to flip it and flip the sign of it. This is just a slide of standard reduction potentials. So obviously you can see some of the half reactions here and the cell potential associated with them. Remember, they are all written as reduction. They're all gaining electrons here. If you want the oxidation, you have to flip it and then flip the sign of the potential. This is not something you would ever have to memorize. And the ones here kind of in the notes, there's actually more here that might not be on the actual printout from the website. So you definitely need to look at these sometimes in problems. Sometimes they might just give you the standard reduction potentials right in the problem. Sometimes you might have to actually look here in your notes at the actual list. Just another slide here showing you some more of these standard reduction potentials. Again, no need to memorize, but you might need to actually look back at this and use this for problems. They're all written as reductions, remember. If you need the oxidation, you actually have to flip the reaction here and flip the sign of the potential. If you want to calculate the cell potential of the entire cell, right? So we say E naught cell because that's going to be your cell electrical potential here under standard conditions. You just take your E naught for oxidation and add it to the E naught of reduction. Essentially, take your oxidation potential, add it to your reduction potential here. It's very simple math, all right? You just have to remember and be careful here that you might need to flip the sign for the oxidation because we're given a list of standard reduction potentials. Something important to note here, very important idea that you need to understand. If you have a reaction here and they don't actually give you the reaction, there's no reaction given, so you can't look at a reaction and see who's being oxidized and who's being reduced, the metal that is more positive gets to be reduced. So if no reaction is given, and you can't look at the reaction to figure out who's being oxidized, who's being reduced, the one that's more positive gets to be reduced, and then the other potential would be the oxidation, and you would have to flip it. So that's a very important idea here to understand. If no reaction is given, when you look up your potentials for each half here of your cell, the one that's more positive gets to be reduced. But if the reaction is there, you just got to look and see which substance is losing electrons, which substance is gaining electrons. Then you would know which is being oxidized and which is reduced. But if no reaction is given, the more positive one gets to be reduced. Very important idea that you need to know. But we can easily calculate the cell potential here just by adding up the two cell potentials here for your oxidation and your reduction. So here's just a list of steps that you would use to calculate the cell potential here for a voltaic cell. You figure out which element is oxidized and which is reduced using your reaction if it's given. So you can look at the reaction and see who's losing, who's gaining. If you don't have a reaction, the one that is more positive gets to be reduced. So when you look up your reduction potentials, the one that is more positive of the two stays as reduction. The other one gets flipped, becomes oxidation, and you flip the sign of it as well. You would write out both equations with your voltages. Remember, you're going to reverse the equation that will be oxidized and then flip the sign of that one as well. You will balance the half reactions, but the interesting part is here, you never multiply those potentials by a coefficient. If you need to balance a reaction and multiply a half reaction by a coefficient, you do not touch the cell potential there. You don't do anything to the cell potential, right? Because it's a ratio, by multiplying it by a number, it doesn't affect the cell potential here. So that's a big idea. If you flip a reaction here, you have to flip the sign. That's all you could potentially do to the cell potential here of one of these half reactions. But you might need to multiply a reaction by a number in order to get everything to balance up, but you would not do anything to the cell potential when you do that. That's a big idea here. And then once you kind of get everything good to go, you will add up your half reactions to get your overall reaction, and then you would add up those voltages. But the biggest mistakes people make here, when you flip the reaction to do your oxidation, you have to flip the sign of the voltage. And just because you need to multiply a half reaction by a number, you don't do anything to the voltage itself. So just be very careful here and don't fall for any traps. Let's look at a simple first example here. This one says we have a voltaic cell based on the following two standard half cell reactions. We want to calculate E naught here. Okay, so they are giving us, if you notice, these two standard reduction reactions here. Both of these substances are being reduced. They're gaining electrons here. I'm not given the overall reaction, so I can't figure out who's being oxidized and who's being reduced from that. So I need to look up the standard reduction potentials here, and the one that's more positive is going to stay as reduction here. So you have to find these on your standard reduction potential list. We're not given the voltages, so you have to actually look these up. So you will need to reference that list and be careful. Make sure you're actually finding the one we're looking at here, right? Because sometimes they have different charges and stuff, so you need to actually find the ones we're looking at. When you look for the cadmium 2 plus adding 2 electrons here, forming cadmium solid, when you find that on the list of standard reduction potentials, it has an E naught equal to negative 0.40 volts here. All right. When I look up the tin 2 plus gaining 2 electrons, forming tin solid here, I see that that one has an E naught equal to negative 0.14 volts. Okay, so these are my two reduction potentials for these two half cell reactions. So because I don't have the overall equation, I need to look at them and realize that the more positive one is going to be reduced here. Okay, so of these two, the negative 0.14 volts is more positive. They're both negative, but the tin one is more positive. So that one is going to stay as reduction. That means the cadmium one is going to be the oxidation and would actually need to be flipped here. So they're not asking me to actually write the overall reaction. So as long as I know that the cadmium one needs to be flipped, I just need to flip the sign here now. And now I can just add up these two voltages here to get my voltage for the overall cell. When I do that, you can see that you end up with 0.26 volts here. Your units are going to be volts, so make sure you have them. All right, but this was a pretty simple problem. You just had to look up the standard reduction potentials for each from the list. Because we didn't have the overall reaction, the one that was more positive stayed as reduction, then the other one had to be flipped, and we would flip the sign. But we didn't have to do the overall reaction, so we just flipped the sign and then added them up, but remember to include volts here. So the cell potential for this cell that is set up under standard conditions would be 0.26 volts. Let's look at another example here. This is telling us to consider this galvanic cell based on this reaction. So we are given the reaction here. So I can use the reaction to figure out who's being oxidized and who's being reduced. I have to give the balanced cell reaction, calculate the E naught, and write that shorthand diagram or the line notation here. So first thing I'm going to do is look at the equation. I see here that on the reactant side, I have Al3 plus going to Al solid. So it's going from a 3 plus to a 0 charge. All right. So if it's going from a 3 plus to 0, that means the aluminum is gaining electrons. So the aluminum here is going to be the reduction. And then just confirm your magnesium on the left side is going from solid, which would be 0, all right, to 2 plus on your product side. It's losing electrons and becoming more positive. So the magnesium is going to be the oxidation because that is the loss of electrons. So now I know which is being oxidized, which is being reduced. So I know that when I look up here, the standard reduction potential for the Al3 plus, that one's going to stay as reduction. It's going to stay as the way it was written kind of on the list of standard reduction potentials. So that one, when I look it up, you see we will have Al3 plus the 3E minus, it's gaining electrons here, it's being reduced, going to Al solid. And the E naught for that is equal to negative 1.66 volts here. All right, because I have the actual reaction, I can use it to figure out who's being oxidized and who's being reduced. I don't use the more positive trick here. All right, so the aluminum has to be written as reduction, which he's written as gaining electrons here, which is exactly the way it's written on the standard reduction potential list. But then that means the magnesium is going to need to be flipped when I look it up on the table because it's being oxidized. So I look up the magnesium half reaction here on that standard reduction potential list. If you need to go grab the list and look at it, make sure you're doing this. You need to be able to do this. All right. So the magnesium is going to be magnesium solid here. All right. Going to Mg2 plus 2E minus. The electrons are being lost. This is oxidation. So the E naught here is going to be flipped from the E naught that you get on the table because that's written as reduction. So when you flip the sign here, the E naught for this is 2.37 volts. All right. So you need to remember to flip the one that's being oxidized and flip the sign here. It does want us to give the balanced cell reaction. So I need to make these electrons cancel out. So it looks like the only way I'm going to do that is if I get them to be 6. So I'm going to have to multiply the first one by 2. So I'm going to end up with 2 Al3 plus 6 E minus and then 2 Al solid here. But remember, when you multiply a half reaction, you don't do anything to the E naught because this is a ratio here. So multiplying by a number doesn't do anything to the cell potential here. Don't fall for the trick. And then the magnesium half reaction is going to have to be multiplied by 3. So I'm going to have 3 Mg solid, 3 Mg2 plus, and then my 6 electrons. So now I'm ready to add up this reaction here to get the overall balanced cell reaction. Obviously, the electrons cancel out, which is what the point of this was. So I have, in this case, the 2Al3 plus, realize this would be aqueous, all right, plus the 3 magnesium solid here. These phases are important because this is essentially telling you what the charge these things are going to be. So the magnesium solid here is a 0 charge essentially. Going to the 2Al solid plus the 3Mg2 plus aqueous here. So this is my overall balanced cell reaction here. It's completely balanced. You can check it if you need to. The charge is balanced. Everything's good. Now I'm ready to calculate the E naught. I just have to add up the cell potentials here for each of the half reactions. When I do that, I get 0.71 volts. So that's going to be my cell potential here for the cell. But the last thing it wants me to do is do the shorthand diagram here, which would be the line notation. Remember, you have to write the line notation with your solids kind of on each end, and you need to have the anode going to the cathode. So on the left should be your anode, cathode should be on the right. So in this one, if you need to kind of think about this, remember the anode is where oxidation is occurring. So we know that the magnesium is where oxidation is occurring. So this would be your anode. And then cathode is where reduction takes place, or the gaining of electrons. So then this one would be your cathode. Get used to labeling which one's being oxidized and reduced. Get used to labeling the anode and cathode here. It helps you stay organized, especially if you have to actually draw this. So now I have to write this line notation or shorthand diagram. So I need the anode on the left. So the solid is going to be on the left. So I have my magnesium solid here on the left, separated by your phase boundary. I'm going to have the Mg2 plus being the solution here. Remember, you have to indicate that it's 1 molar because you're at standard conditions. It's separated by your salt bridge. Then you write your other solution here. So my other solution would be the Al3 plus. That's 1 molar as well, separated by the phase boundary. And then finally, you have your other solid here, your aluminum solid. But your anode is on the left, your cathode is on the right. You're flowing from anode to cathode, essentially. So we took care of everything that was asked here. We did the balanced cell reaction. We calculated the E naught of the cell, and we wrote the shorthand diagram or line notation. So this is something you need to be able to do for any reaction or any half reactions that are given. For this example, we are going to consider the galvanic cell based on this reaction. So we're given the reaction, so we can figure out who's being oxidized and who's being reduced from the reaction itself. We want to do the balanced cell reaction, calculate E naught, and we want to diagram the cell and label this completely. All right, so let's start by looking at the reaction here, figuring out who's being oxidized, who's being reduced. So the first thing I notice is I have this Ag with a plus, so it's 1 plus going to Ag solid, so it's a 0 charge on the right. So 1 plus to 0, well, that means it's going to be gaining electrons here. So the silver is going to be reduced. So that's going to be the cathode, essentially. And then the zinc, let's just confirm, this should be your oxidation. It's going from 0 to 2 plus. It's losing electrons. So that is your oxidation. So now I can use the reaction there to figure out who's being oxidized, who's being reduced. Now I need to look up the half reactions on the standard reduction potential list. I already know the silver's reduction, so it's going to be written as is on or from the list here. So I have the Ag plus 1E minus going to Ag solid. That's reduction because it's gaining electrons. It's written as is from the list. So our E naught here for that is going to be 0.80 volts. But then for the zinc half reaction, when you look it up, you need to flip it and flip the sign because this is your oxidation and the list is in reduction potentials. So when you look up the zinc and you flip it, you get Zn solid here going to Zn2 plus 2E minus. And this makes sense because this zinc is oxidized or losing electrons, and this would be losing electrons here. But then when you get your E naught for that one from the list, you have to flip the sign because we flipped the reaction. So we have 0.76 volts here for that one when we flip the sign. We need to do the balanced cell reaction here. We need the electrons to cancel. So it looks like I can make them cancel by getting the silver half reaction here to 2 electrons. So I'm going to multiply that one by 2. So 2 Ag plus. Now we have 2E minus and 2 silver solid here. Now the electrons will cancel. So I can add this up. Obviously, electrons are gone. So when I write what's left, I have 2Ag plus, this would be aqueous here, plus the zinc solid going to the 2Ag solid plus the zinc 2 plus aqueous. So that's the overall balanced cell reaction here. You can double check it to make sure it's balanced, make sure the charge is all good, but that's your reaction here. Remember to include the solid and aqueous. We need the E naught of the cell, so we're just going to add these two together. We get 1.56 volts. Don't forget your units. So this takes care of the balanced cell reaction and calculating the E naught of the cell. Now we need to actually draw the entire diagram here and label it completely. Before I do that, I want to make sure I label my anode and cathode here. I know that anox, oxidation, is going to be the anode. So the zinc half reaction is your anode. And then the cathode here, red cat. All right, reduction is taking place at the cathode. All right, so that's going to be labeled because that's going to be important for my picture. Now I can actually go through here and diagram this cell. When you have to diagram one of these voltaic cells, there's a lot of stuff here that you have to show and you have to make sure you're including kind of in your picture here. So the first thing you need to realize is, okay, they need to be in separate containers here. That's the first big idea. We don't want to just generate heat here. We want to generate an electric current here by having them separate and allowing those electrons to flow through the wire. Another thing people mess up here, you need to actually have some kind of solution in your actual beaker here, or your container. You can't just label it as having a solution. You have to actually show that it's in solution. We're going to have one of our metal cathodes here in this one. We're going to have the other metal cathode here in the other one. It doesn't have to be, you don't have to be Picasso here, but you do have to have all these things kind of shown and labeled. So let's start with the anode here. All right, it doesn't matter which side you put things on as long as you know which side's the anode and which side's the cathode and which way everything's flowing. So I'm going to put the anode on the left. I already labeled my zinc half reaction here as the anode. So this would be the solid zinc. And then obviously the other side would be the solid silver here. These are going to be connected, all right, through a wire, and there's going to be a voltmeter here in between, and that voltmeter is going to show the current that is flowing. So we already calculated the E for the cell, so this would show 1.56 volts here. That's indicating that this is generating an electric current. This is a voltaic cell here. Since I have the wire written and I know which way these electrons are going to flow, I can show which way they're going. They're going to go from the anode to the cathode here alphabetically. So you would show that the E minus are going in this direction here. Very important to actually label the anode and cathode as well. So I know that this is going to be the anode. Remember here, the anode is negative, and then this side is going to be the cathode. And remember, that's going to be positive. So definitely need to label the anode, label the cathode, show the flow here. I need to also show what's happening here in the solution itself. So I know that if I have zinc on the left, my solution, if you look at your reaction, the zinc was going to zinc 2 plus. So I need a 1 molar solution here of zinc 2 plus, and you have to indicate that it's 1 molar. Right? You don't have to indicate that it's like, zinc nitrate, but as long as you understand that it's going to have ions of zinc 2 plus in it and that it's 1 molar. The other side here is the silver. According to the problem, it was silver 1 plus. So this is going to be Ag plus, and it has to be labeled as 1 molar. So that's your solution on the other side. Don't forget the salt bridge here, right? You do have to show the salt bridge kind of entering both of these. It does actually have to go into the solution for each. Again, this is not the perfectly drawn salt bridge here, but you can see that there is a salt bridge here between the two, and you need to actually know which way the ions are going to go. So I'm going to use KNO3 in my salt bridge. Again, it's an easy one to use because you know it's not going to form a precipitate. The potassium is always going to be soluble. The NO3 is always going to be soluble. It will never cause a precipitate here. You need to understand that on the anode side, as the zinc solid is losing electrons, you're forming zinc 2 plus, getting a buildup of positive here in the solution. So I need the opposite charge to come in from the salt bridge. So the NO3 is going to be going toward the anode side. So you can kind of see that here. I'm trying to show my arrow indicating the NO3 is going into the anode side, the NO3 minus. But then on the cathode side, you have the Ag plus gaining the electron, forming solid silver. So you have the plus ions being lost. All right. So you have a buildup of negative. So you need the K plus from the salt bridge going into the cathode side. All right, so you definitely need to show that. In order to get full credit for something like this, you have to pretty much have all of this shown that you see here. So there's a lot here, so pay attention to this. You have both metal electrodes, you have them both in separate containers in a solution of an ion itself that's listed as 1 molar here. You have the anode and cathode explicitly listed. You're showing that you're generating the current. You show which way the electrons are going, and you show which way the ions are going from the salt bridge here. So in order to get full points, this is everything you would need to show if you have to diagram one of these voltaic cells. So be very careful with this. Make sure you can do this for any example that you're given. It's definitely a big idea here, showing that you understand what's happening for the voltaic cell. Now let's talk about favorability here with these electrochemical cells. If you calculate your E naught and it's positive, then that cell is thermofavored. All right, if your E naught is positive, you have a thermofavored cell, and it's just going to happen on its own here. It's generating an electric current. If your E naught for the cell is negative, that's a thermo-unfavored cell. All right. And if your E naught is actually 0, you're at equilibrium. Essentially, you have a dead battery. We can use E naught to actually calculate your delta G here, calculate your Gibbs free energy. And the equation here is delta G is going to be equal to negative NF E naught. This is given on your equation sheet. E naught here would just be the standard potential here of the cell. You would basically calculate that like we just did. You need to understand here, though, that it's going to be in volts, and a volt is the same thing as a joule per coulomb. All right, that's very important because in order to make our units cancel here, you need to know that a volt is the same thing as joule per coulomb. F is Faraday's constant. It's 96,485 coulombs per mole. This is given directly on the equation sheet. And then this N here is the number of moles. Essentially, it's the number of electrons that are transferred in the balanced equation. Very important here. Basically, when you add up your reaction and your electrons cancel out, what is that number? And that's your N here. So if you have all this, you get the number of electrons from the balanced equation. F is a constant, and you use your standard potential here that you calculate. You can calculate here the delta G for a particular cell. But you need to realize here that E naught is going to be in volts, and volts is the same thing as joules per coulomb. That will allow your coulombs to cancel here from the Faraday's constant, and your units for this will actually end up being in joules per mole when you calculate your delta G. And then the same things apply. If you get a negative delta G, you know that the reaction is thermofavored. If you get a positive delta G, then you know it's thermo-unfavored. But definitely understand that a positive E for the cell when you calculate it means that the cell is thermofavored. A negative would be thermo-unfavored. But you're going to have to use this equation to be able to calculate some things here. The first example we see here is actually pretty easy. We want to calculate delta G for this reaction under standard conditions. They gave us the entire reaction already balanced, so that makes it very easy. And we already have the E naught given as 1.56 volts. All right, so we basically already have everything we need here. We're just going to actually need to go and plug in. So our equation here is going to be delta G equal to negative NF E naught. So if we're solving for delta G, N is the number of electrons here transferred in the balanced reaction. That's going to be your N, your number of moles. Well, realize here, if you're looking at this, okay, you can see that your silver has a 1 plus charge, but the zinc was 2 plus. So if the electrons were to cancel here, the only way they would cancel is if you had 2 electrons for each, because the zinc is going to have 2 electrons involved with it. The silver would just have 1 electron. That would have to be multiplied by 2 to make it 2 electrons, and that's when they would cancel. So our N here, our number of moles, is going to be 2 based on the number of electrons that would cancel out in the balanced equation. If you don't believe me, write each half reaction, look at the electrons. The only way they would cancel is if there were 2 electrons. All right, so we're going to have negative here, 2, all right, times F is Faraday's constant, 96485 coulombs per mole, times E naught, which we were lucky, they already gave us this. Sometimes you have to actually calculate this. It was 1.56 volts, which is the same thing, remember, as joules per coulomb. You need to know that here. A volt is the same thing as joules per coulomb. So when you do your math, notice the coulombs would cancel, and your units are going to be joules per mole here. So when you plug and chug this, you should get negative 301,000 joules per mole here with correct sig figs. All right, so that's our overall answer here for delta G. The negative tells us that this reaction is thermo-favored. We kind of already knew that, though, from our E naught. The E naught being positive told us that this was thermo-favored as well. So this was pretty simple, just being able to calculate delta G with everything already given. Let's look at a more fun example here. This one says, what is the equilibrium constant for the following reaction at 25 degrees Celsius? So we're given this reaction here, and we want to find the equilibrium constant. Before you panic, you need to remember something here kind of from the last unit. If you remember, we could use the negative Ratlink equation to find the equilibrium constant. Well, that involved delta G. So if we can get delta G here, we could find, all right, the equilibrium constant. Well, in order to get delta G, when you have one of these oxidation reduction reactions here, you're going to have to actually use that negative NFE naught. So if I can calculate the electrical potential here for this cell, I could work on getting delta G, which then I could use to get the equilibrium constant. So you really have to think this one through. You actually want the equilibrium constant, but you have a lot of things you need to do here in order to be able to get that. All right. Something else I just want to point out here, if you look at the reaction, we have a reaction given. So we have to use the reaction here to figure out what's being oxidized and what's being reduced. All right. If you look at the actual reaction, the Fe2 plus is going to Fe solid. So that's going to be gaining electrons. So this one is reduced. That means the silver here is going to be oxidized. It's going to be losing electrons. It goes from 0 to plus. That makes sense. And the note I have here is, according to the reaction, the Fe2 plus is being reduced. All right. Even though if you actually look up these standard reduction potentials on the table, all right, the silver has a more positive value. But we only care about which one is, more positive being reduced when we don't have the reaction given. So because I have the reaction given here, I have to look at it to determine who's being oxidized and who's being reduced. All right, make sure you pay attention to that. If the reaction is given, use the reaction to figure out which is being oxidized and which is being reduced. So now I'm ready to write my half reactions here because I need to calculate that E naught. So according to what I just labeled, the Fe2 plus is going to be reduced here. So I need to actually write that as is from the standard reduction potential list. So I have Fe2 plus 2E minus going to Fe solid here. And the E naught for that, when I look it up, is negative 0.44 volts. According to the reaction, that one's being reduced, so it stays written as reduction, gaining electrons. But then the silver, all right, is going to have to be flipped when you look it up because it's being oxidized. So I'm going to have Ag solid here going to Ag plus 1E minus. That's a loss of electrons. That's being oxidized, but I flipped it. So I need to flip the sign here of the E naught from the standard reduction potential list. So it's going to be negative 0.80 volts. I do have to, write my overall balanced equation here just to confirm the number of electrons. So if you look, I'm going to have to multiply the silver by 2 in order to make the electrons cancel here. So then everything else should be good. Once I cancel out my electrons, I get my 2Ag solid here plus Fe2 plus aqueous going to 2Ag plus aqueous here and plus the Fe solid. And that's the equation that I'm kind of using here based on what I'm given. So it looks like this is good to go. Keep in mind you did have 2 electrons here in your overall balanced equation. So that will need to be your N value when you plug in. So let's calculate this E naught here. When we total these up, we do get negative 1.24 volts here. So obviously this is negative for our E naught. We know this is not thermo-favored, right? But all I did right now was calculate the E naught. I have to keep going here with this problem in order to eventually get to the equilibrium constant, but I have a few more steps along the way. Now that I have the E naught, I can use the delta G equals negative NF E naught here to find delta G. So when I plug everything in, delta G is going to be equal to negative, N was 2. There were 2 electrons that canceled out in our balanced equation. We saw that, times the 96485 here, coulombs per mole. Faraday's constant, you can get it right off the equation sheet, times E naught, which we found to be negative 1.24 volt. Volts is the same thing as a joule per coulomb. So it's negative 1.24 joules per coulomb here. Our coulombs will cancel. Our units will be joules per mole. Pay attention to your units. So when I plug and chug this with sig figs, you should sig fig as you go here. 239,000. All right, so 239,000 joules per mole. Watch your units here, okay? So this is just my delta G. I haven't gotten to the equilibrium constant. Remember, now you will have to use the negative Ratlink equation. So delta G is equal to negative RT ln of K here. Remember, you are going to need your temperature, but it needs to be in Kelvin. So we have our 25 degrees Celsius plus 273, giving us the 298 Kelvin here for our temperature. Our delta G is in the correct units here. Remember, R is going to have units of joules per mole times Kelvin. So this is right from the equation sheet. It's that version of R. So we want delta G to be in joules per mole here, so we're good to go. We have 239 and then 000 joules per mole equal to negative R. R was the 8.314 joules per mole times Kelvin version. All right, this will make our units all work out here. Times the temperature, which we said is 298 Kelvin. Make sure you're in Kelvin here. And then we have the ln of K here, which is what I'm looking for, the equilibrium constant. So you just have to do your math. Remember here, if you need to actually look at the steps, first thing you would do is multiply your two terms, essentially your R and your temperature here, divide what you get for that by both sides, and then you need to do the second ln button times your answer here, and that will give you K. So you're going to multiply these two terms together first, whatever you get for that, divide it by both sides. That would be equal to the ln of K. So you do second ln button to that answer, and then you will actually solve for K here. When we do that, if you do it correctly, I would make sure you can do the math. You get K being equal to 1.28 times 10 to the minus 42nd. So before you panic and think, oh my goodness, I can't have a very high or very low answer, absolutely you can. Don't get too worried about that. This is telling us here, now we can analyze this. This is saying here K is very, very, very small. So products over reactants, you have a lot of reactants present. That's the only way you can get a very small K. And that makes sense because the forward reaction here is not thermofavored. We have a positive delta G. We have a negative E naught. So we know the forward reaction is not thermofavored. The reverse reaction would be. So we have a lot of reactants present here at equilibrium according to the K value. So this is something you need to be able to do. Take kind of an electrochemical cell, find E naught, use that to find delta G, and then use delta G to find the equilibrium constant. You're kind of tying together here a bunch of different ideas. So make sure you can do a problem like this. Last thing I want to talk about here real quick is, what we can use these voltaic cells for. Remember, they are thermo-favored cells, so they will just happen and generate an electrical current here on their own. They can be used here for batteries. All right, we can use this for car batteries here. They're going to generate the electrical current when you need it. We could use dry cell batteries involving a paste. So you can see here kind of the basic setup, maybe one of the batteries you might have to use in electronic devices. We can even use this for fuel cells. These reactants will be continually supplied, like in spacecraft, and we can generate our electric current using that. So just something to realize here is that these galvanic or these voltaic cells are thermofavored, so they are generating an electric current. Essentially, they are a battery. Right? They provide the basic idea of what a battery is here. Obviously, batteries can be more complex than the galvanic cells that we draw in the separate containers, but the ideas are there, and you need to know that these voltaic cells are generating an electric current.